Hello again, this is Dr. James Camp from Lee College in Baytown, Texas, and this is the second part of my commentary on Chapter 7 of Big C++ by K. Horstmann. Today we're going to be going over C strings and structs in C++. Okay, C++ has two ways of handling strings. What you've done so far is the string class. Okay, it supports character sequences of an arbitrary length. You can start with hello, you can add world to it, and it just automatically expands to contain however much text you want to add to it. And it provides some convenient operations like plus and double equals and less and greater. So all in all, it's a much more convenient way of using, it's a very convenient way of using strings in C++. However, if for any reason you need to write code that has to be compatible with old style C, or if you find yourself writing some old style C code, because C++ programmers are often asked to go back and program in C once in a while, you need to understand how a C string works. Okay, to understand a C string, you have to understand what a character is. An individual character is one printable item. I usually describe it as one entity that you can type from your keyboard. So a 3 or an A or a $sign. What's stored in a character type variable in C++ is actually the 7-bit ASCII code for that character. You may remember we've talked about the ASCII table before. ASCII was the American standard for computer information for a very long time until the Unicode standard came around and replaced it. C++ is not fully Unicode compliant. C++ strings, string objects can hold Unicode characters, but a standard char type variable holds an 8-bit value, which is typically a 7-bit ASCII code. You can see that in decimal, ASCII runs from 0 to 127, and that first we have a bunch of punctuation characters, then we have the numbers, then more punctuation, then we have the capital letters, then some more punctuation, then the lowercase letters. So it's important to know that an uppercase letter always has a lower ASCII value than a lowercase letter. So if you're sorting strings, for example, the uppercase is always going to come before the lowercase. Okay. What if you want to type one of these characters that doesn't exist on the keyboard? Or that, in the case of backspace, typing it on the keyboard will actually just erase a character on your computer screen. Or hitting tab on the keyboard may just insert some spaces in your code. You can put a backslash followed by several single character codes that indicate, these are what we call escape sequences. So /0 is called the null character. It's an ASCII character whose value is 0. It does not print anything. It does not do anything. It's just there to hold the value 0. You can put tabs in your code with /t. You can put new lines in your code with \n. You can make an audible bell sound from your terminal window with a \a. And then, of course, because backslash itself is now used for escape sequences, you have to put 2 backslashes in a row if you want an actual backslash character in your code. And then for reasons that involve the fact that they have other uses in strings, backslash single quote, backslash double quote, and backslash question mark exist as well. Here's how you would type some character literals. note that a single character in C++, if you want it to be interpreted as a char type variable, gets single quote marks, not double quote marks. So single quote y is the character y. Single quote 0 is the character for the digit 0. It will print 0 on the screen. Single quote \0 is what we call the null character. Character 0, a character that does nothing except end strings in in old style C. Note that if I put double quotes around y, it will not be interpreted as a char value, but as a C string, as an array of 2 character values, y followed by a null character terminator. That will be interpreted as a string. Okay. The C++ string type, what you've used so far for strings, is an object, very much like the vector type that we've used, okay? Because of the way objects work, a C++ string knows how long it is. It has data embedded in it that stores its length. In the C language, there are no objects, okay? That's what the plus plus for C++ comes from. The way to store a string in standard C is just an array of type character. So you might have an array of length 10 and store HELLO exclamation point in that array. But how is C supposed to know where that string is, or where that string ends, how long the string is? It might keep reading. Spaces 6, 7, 8, and 9 in this array are not empty. They just have gobbledygook values. They have values that haven't been initialized yet. Yes, gobbledygook. So the easy answer is to add one more null character to end the string, and now it looks like this. You have HELLO exclamation point, and then character 0, the null character, telling us that the string is ending there. And so in that case, C will not keep reading, and it won't look at the uninitialized values in 7, 8, and 9. Okay, so the null character in a C is always the last character in a C string. So in C, if we give the literal value quote cat, it really gets interpreted as 4 characters, C, A, T, and null character. Even in C++, string literals are always interpreted as null terminated character arrays for backwards compatibility with old style C. Okay, since it's really an array, a string literal can be assigned to a pointer variable that points to the initial character in the array. Okay, when you put quote Harry in your code, what you're really doing is creating an array in memory of HARRY and \0, the null character. And if you put char star char pointer equals Harry, char pointer ends up pointing right at the letter H. And as we know from how pointers and arrays are interchangeable, this is the same as creating an array of characters that points it at the string Harry. Okay. The standard library from old style C includes a string library. We call it C string in C++. And it includes a lot of functions that work with C style strings. So strlen is going to count how long your string is until it reaches a null character, and then it's going to return how many non-null characters are in that string, or how many characters there are before the null character. Because a C string is just a array, you can modify it using any of the standard ways that you can modify an array. So if we typed name at 0 equals L, we're going to change Harry to Larry. Okay, the C standard lib header includes the function a to I, a meaning a character, I meaning an integer. So you can pass a character pointer pointing to a null terminated string, and it will do its best to convert that into an integer for you. Okay. You can use this function you can use any of these C string functions by getting the C string equivalent of a C++ string. So if we have a C++ string called year, we can call its member function .c_str, which is read as .c string, and that will pull out the C string equivalent of that string. Okay. To convert from a C string to a C++ string going the other direction is also easy. Okay, the assignment operator does it automatically. So if we have char star Fred equals Frederick, then all we have to do is say string name2 equals Fred, and that conversion is done automatically. Note that C++ strings also allow the use of the square bracket operator as if they were arrays. So you can change Harry to Hardy, Mary to Mark, all sorts of fun things like that. Perhaps more useful might be using this to convert characters from lowercase to uppercase. There's a toUpper function defined in the C character type header, and a toLower function that does the opposite. In conclusion, here are some of the useful C string functions from the C string library. strlen returns the length of a string. strcopy copies the characters from string S into string T.strincopy is a safer version that allows you to make sure that you don't overwrite the bounds of string T. If T is, say, length 10, you would put N as 9 so that you still have room for the null terminator. strcat concatenates string T and S.Strincat, again, is a safer way of doing that doesn't overwrite string T, or doesn't overwrite the bounds of string T. And then string comparison returns 0 if the two strings S and T are the same. It returns a negative number if S is less than T, and a positive number if S is greater than T. Okay. It kind of goes without saying that C++ strings are easier than using the C string functions. The only real reason you would use the C string functions is if you have code that requires you to, is if your application requires you to be compatible with old style C code, or if for some reason you had to actually go back and write some old style C code, maybe for your Unix programming class in an upper division computer science degree or something. Okay. A program's memory is separated into two pieces, the stack and the heap. Okay. The stack contains your program code, then it contains all the variables that you allocate for main, and then it contains all the variables that you allocate for any other functions that you call. And as you add more functions, as you call more functions can get put on the stack. That's why it's called a stack. They stack up on top of each other. There's also a giant area of memory available to your program called the heap. And this is for what we call dynamically allocated memory. You may not know beforehand just how many values you need in an array, for example, or how many objects you need in an object-oriented program, or whatever. To solve this problem, you can use dynamic memory allocation and ask the C++ runtime system to put new values on the heap whenever you need them. Okay. The operator that creates dynamically allocated memory in C++ is new. New double open bracket in close bracket creates an array of size n and yields a pointer to the starting element. Okay. This is cool because in this case, n does not have to be a constant. You can ask the user, how many grades do you want to input? And they can type in 35, and you can create a new array of size 35. Okay. You can also create new pointers that are not arrays by just saying new double without the square brackets after it. And that will create a new, say, bank account balance or something for you. When your program no longer needs the memory that you asked for with a new operator, you have to return that free memory to the heap using the delete operator, okay, or the delete with square brackets operator for arrays. If you don't do this, you end up storing unused memory in your program, and that makes your computer slow down, be less efficient, that sort of thing. That's called when you create memory and forget to delete it later, that's called a memory leak. Okay. After you delete a memory block, you can no longer use it. Okay. Your computer is very efficient and quick at reusing, recycling memory locations. So be sure that you don't delete an account array and then try to use it. Okay. You no longer own that memory. It's probably already being used for something else. Okay. We have an algorithm here for resizing an array. I'll let you look at that in the textbook if you want to see how it works, but essentially the idea is when your array fills up, you dynamically allocate a new array that's twice as big, and then you copy all of the elements from the old array to the new array. This is basically how vectors and string objects work as far as allowing you to change their size. Okay, we just talked about memory leaks. Some common errors with dynamic memory allocation. P was never allocated with new, so you can't delete it. In the second one, P is new. P is allocated as a new int, and then you try to create another new int without deleting the first one. That's going to create a memory leak. Okay. The third one, P is created as an array of integers, but then it is deleted without the square brackets. Okay, so you're only going to delete the first part of P, you're not going to delete the whole array. In the fourth line here, P is created as a new int, Q points to P. Q does not get a new block of memory, so you can't delete Q after you've deleted P. Okay, Q and P both point to the same memory. You can't delete the same memory twice. Okay. If you have a pointer that points to a new integer and then you delete it, and then you try to remember, you maybe mess up in your code and you try to assign it a value later, that's a runtime error that's going to crash your program. The way to make sure you don't do this is after you delete a pointer and you're left with a dangling pointer, we call it, you then assign it the value null pointer, which will still throw up an error if you try to assign it something, but it won't mess up your program in quite the same way. Okay. So, dynamic memory allocation rules. Every call to new must be matched by a call to delete. Okay. Every call to make a new array has to be followed by delete with square brackets. Okay. Always assign null or null pointer to the pointer after deletion, and don't access a memory block when you don't own it anymore. Okay. If you don't follow those rules, your program can crash or, perhaps worse, run unpredictably and give you bad output. Okay. We can also use pointers in arrays. So if we said int star pointer array, that fills an array with pointer types. We can also make a vector of type int star and get pointer vectors. Why is this useful? Jagged arrays are possible, arrays that are not perfect squares of 3x4 matrix or something. You could have 10 rows, but each row is allocated dynamically as a different sized array. You can make a little Christmas tree or something. Okay. You can also dynamically allocate large data. Okay. If you create an array in C++, at runtime, it allocates all the memory for that array. But what if you need to hold a bunch of strings, a bunch of large objects that have a lot of data in them? It's handy instead to make an array of pointers to those strings or those objects and just allocate the data they point to on the heap as you need that memory allocated. Here's an example of a jagged array. This one they wanted to have the number of columns equal whatever row you're currently on. So the first row has one column, the second row has two columns, and so forth and so on. You would waste twice as much memory if you just made this a standard two-dimensional array. So it's better to create this as an array of pointers and then dynamically allocate an array for each pointer. All right. Switching gears completely, we're now going to talk about another way to store information in C++, which is a structure. So far, we've used arrays to hold lists of related values. Okay, we might have a list of angles, or a list of launch velocities, or a list of birth dates, or something. But what if the values have different meanings? Okay, what if we want to store an array of heights and an array of widths? Or if we want to store hours, minutes, and seconds for timestamps? Or if we want to store the area and the volume for a shape. We could create arrays that hold, every odd one is a height and every even one is a width, but that gets kind of complicated to deal with. But what if we had values of different types? What if we have a street number and a street name? What if we have a name and a GPA for a student? What if we have your Zoom number, your password, and your time of appointment for a Zoom meeting? We couldn't store those as an array because they're different types. Now we could create parallel arrays where you have an array of street numbers and an array of street names, and the entries at numbers at 2 goes with the entry at names at 2, right? But that also gets complicated to deal with. What if we could have a single variable that held mixtures of data? Okay, in C or C++, we call that kind of variable a struct. Okay, we define a structure type with the struct reserved word, as in struct street address, Okay. And then within that struct, we have individual lines. Each individual line creates a new, what we call a field or a member of our struct. So this struct has field house number that's an integer and field street name that's a string. Note that when we define struct types, we tend to name them using what's called camel case. That is, we start with a capital letter and then every new word begins with another capital letter looking sort of like the humps on a camel. That's why it's called camel case. We don't tend to put underscores in struct names. Once you've created a street address, you can use it as a type name to declare a new variable, street address, White House. And then you use dot notation to access the members of the struct. So White House dot house number equals 1600. White House dot street name equals Pennsylvania Avenue. Here's a more complicated structure, the TM structure that's used in many of the ctime functions. Okay, here every member is an int, but they each have a different meaning. So TM dot TM sec means seconds after the last minute. Okay, you can assign one structure value to another. So if dest equals White House, a complete copy of White House is made and assigned to dest. Okay, that's equivalent to saying dest.house number equals whitehouse.house number, etc. But you cannot compare two structures for equality. We've not defined an equals equals operator for structs in C++, so instead you have to compare the individual members. Dest.house number equals whitehouse.house number, and so forth and so on. You can, at the time that you create a variable, you can initialize all the values of a struct at once using initialization syntax, okay? Or initialization list syntax. So you have an open curly, and then the first field value, comma, the second field value, and then you'd have more commas and more values if you had a larger struct. Structures can be function arguments and return values, okay? So you can pass a street address to a function print address, okay? You can also have a function that returns a structure. Now, this is cool because so far in C++ we have not been able to return more than one value from a function. But if we wanted to here, we can return a house number and a street name from one function. You could also imagine creating a structure called point that has an int x and an int y, and that way you can return both an x and a y value from a function. You can put structures into arrays, okay? Let's say you add a delivery route. Delivery route at 0 is 123 Main Street, okay? And delivery route at 1 would get to be something else. You can also access a structure value in its entirety without the dot notation. And if you can create arrays of structures, you can also form vectors of structures. So we can push back the White House into our list of tour destinations. Okay, you can have arrays as part of a struct. Okay, so in this case, the string location tells you where we are, and the double values gives you the temperatures for 12 different months of the year. You would get Death Valley Noon dot values, dot values square bracket 2. Okay, so use the dot notation to get the array, and then you use the square bracket notation to get the individual value 82 here. And finally, a struct can have a member that is another structure. Okay, so struct person might have a string name and then a street address, work address. Okay, and as you may expect, you would use the dot notation twice to get Theodore dot work address dot street name is Pennsylvania Avenue. Okay. Try it on your own. Write the code snippets to declare a variable A of type street address, set its house number to 2201, and set the street to C Street Northwest. All right. Finally, there's some special code that comes up when you want a pointer to a structure. Okay. As with all dynamic memory allocation, you can use the new operator to create a new structure. This is handy because some structures get to be very large, and it's better to allocate that memory on the heap than to make it a permanent part of your program's stack memory. Okay. It's tempting to say star address pointer dot house number equals 1600, but that would be incorrect because the dot operator is interpreted first, and we try to find a part of the pointer called dot house number, and that doesn't work. We have to dereference the pointer first. So what you do to make this work is you would have to put address pointer, no, that's wrong too. You'd have to put address pointer with the star in parentheses and then put dot house number. Okay, so we dereference the pointer first, then we use the dot operator. Now, that is so cumbersome that C programmers and C++ programmers hate using it. So in C and C++ both, there's a handy way to dereference a pointer and point to its member at the same time. And that's this arrow operator. Okay, address pointer arrow house number means dereference address pointer and then find its member called house number. Much better to use that. Structs can also have members that are pointers. We can have a street address star office, and this way Harry.office can point to ampersand accounting, and Sally.office can point to ampersand accounting, and so Harry and Sally both share the same office. And if we ever change what room accounting is in the building, because they're pointers, they're automatically updated. Okay. Here's a complete code example. I'll let you look through that in the textbook at your own pace. Okay. Finally, C++11 introduced something called share pointer that automatically reclaims its memory when it's done being used. Okay. This allows for something called garbage collection, where the C++ runtime can actually take care of deleting your pointers when they're no longer being used, instead of you having to remember to do that. This is handy. Feel free to play around with it. We're not going to do too much with it now, except introduce it. Okay. Now it's time to take a programming break. You've got a C string practice on the Blackboard site, and struct practice coming up soon. Okay. Good luck and happy programming.